So last time, after wrapping up add with carry, at least for the non-decimal modes, I probably should go on to subtract with carry, but just to take a break from that for a bit, I think I'll do compare, which is compare accumulator. And that's actually a really useful one, because once you've got a compare and an add, and we can already do branches, you can basically write a for loop, or the machine code equivalent of a for loop, because you compare the accumulator with a certain value, and you branch if it's equal to a certain value, which is what for loops do, or while loops or whatever. So I think I'll do that one. This is another one of those ones that's got all the addressing modes that the subtract supports. It's a bit weird. You'd think it just like does a comparison of the accumulator, but what it actually does is it actually does the accumulator and then subtracts a value that it either got from memory or it got from the program in immediate mode. And then it basically sets some flags based on that. And that's why you get this like setting the negative flag if bit 7 of the result is set, because you actually do a subtraction. So one of the things that was confusing me is what you set the carry flag if a is greater than or equal to m, so the value in memory. Then what you really want to know is, are you doing a sign comparison or are you not doing a sign comparison there? Because that makes a difference to whether it's greater or not. Because if you were doing it signed, negative values could appear different. That was confusing me, but I found this other site that's more clear on it, and it basically says that actually it's doing everything unsigned. So it does an unsigned subtraction for this a minus m, which it then sets the negative flag based on that, and the carry flag is based on a being greater than m, and I believe that is doing unsigned. Is that right? Yeah, it says it here. The comp instruction does not use signed arithmetic. It simply compares two numbers between 0 and 255, treating both numbers as positive integers. So it doesn't care when it's doing, basically we're just saying we don't care about negative numbers. In this case, we're going to do them as positive, but we do have to set the flags correctly based on this result. So we still do that subtract as an unsigned subtraction, but we still set the negative flag based on what we found in that result. And that result is not stored. Just the only thing that's stored are the results of the flags. So this seems simple compare, but actually when you look into it, it's a bit hard. It's a bit harder than you think. Yeah, because it's actually doing a subtraction and the whole signed unsigned thing gets in the way. But at least I think this site actually gives some examples of the way it works, like what the values would be before, the values you could add, and what they would be afterwards. So I could just implement these as tests. This is actually a Atari website, so same chip was in the Atari 8-bit computers. So I think I'll just get on with doing this compare, and compare x and compare y. This is compare accumulator. Compare x and compare y are very similar, except they don't have as many addressing modes. But other than that, they are the same. See how far we get, but maybe just get one of these working today with the unit tests, and hopefully if we get this working, we'll have 8 more. Is it 8 or 9? We'll have 8 more addressing modes, 8 more instructions done. So I'll start by the usual. I'll make a unit test file for this. Okay, so that's the test file set up. Let's just fill in this unaffected registers, which is the I register doesn't get affected, the D, the B, and the overflow flag does not get affected. Is that right? Overflow flag is not affected by this result. Is that definitely correct? Yeah, it doesn't get affected. So that's that. And then what are we going to do? So we want to set the A register. We're interested in just setting beforehand the carry flag, the 0 flag, and the negative flag. Don't want to set those two yet. That's what I did there. This is just, so we'll just do compare immediate to start with. Yeah, let's just do compare immediate. It's 2 cycles, and the value that you want to compare with, let's do one of their examples actually. Their example has the value of 26 in memory. Is that right? Assuming that the memory location contains the value 26. So their first example is that the accumulator has 26 in it. This is decimal. Let's just do it in decimal. I suppose it doesn't matter too much at this point. So they assume that 26 is in the A register and 26 is in the program that we're going to compare it with. It's quite handy having it. Let me make this bigger. I think that's as big as I can get there. So this is, yeah, the effects. So I'll just implement some of these tests that they've got here. It's 2 cycles. We expect the A register to remain unchanged. And we are interested in the carry, the negative, and the 0. And not interested in the other, that's unaffected. So what do we expect these to be? So 0 is set when they're equal. So in this case, we're expecting 0 to be true because we compared 26 with 26. So that should be true. So I'll set it to false beforehand just to try and get the test to break. The carry flag should be set if A is greater than or equal to M. So it's the same. So that should also be set in this case. Carry flag should be set to true. I'll set to false before. And the negative flag should be set if bit 7 of the result is set. So that's the result of the accumulator subtracting the value. And in this case, that value is 0, so the bit 7 won't get set. So we expect that to be false. And we'll set it to true beforehand. Let's just see if their test confirms that. Expect 0 to be true, negative to be false, and carry to be true. So I'll put them in the same order they've got them there, just to make it a little bit more easy. True, false, true. Yeah, true, false, true. That's what I expected from that as well. What we're going to call this test, immediate can compare 2 identical values. There we go. So that's test 1 in their case. So let's just see where we're up to with the compiling. So we just want to implement that, well, define that opcode, so we've got a name for it somewhere. Just put this down here with the arithmetics. Let's call these compare. This one is C9. So this is compare immediate. I think I'll implement that one before I put any further tests in. So let's do that. So we've got one decent test there, I think. Okay. So let's go for the first one, the first comparison. So this is compare immediate. So because it's immediate mode, the thing that we want to compare with, we'll call this operand again though, is it? Because it's the result of a comparison, I don't know. In fact, it's very similar to this, isn't it, here? We'll just copy that. It fetches a byte from the program. And then we need to do the accumulator subtract the operand. And we're doing that without converting any of this to signed values. We're going to do it as unsigned. Now we don't store that value. We just store that as a temp result. And then we set the, what do we do? Let's set nothing to start with, and let's just see where we get to with that. Local variables, initialized but not referenced. Okay, let's use that then. So let's set the negative flag based on that one. It is temp and, because we do have a function to, what is it, that can set 0 negative flags, but actually it's based on, what does it do? Could we just call that? Oh, I see, this is setting the 0 based on this being 0, but actually we want to set this based on it being the same as the other value. So that's not what we want there. But as we are going to keep doing this, I'll refactor that later, but we probably do want to do that in a different way. We'll probably want a function to do that. So if we do, does that set the negative flag correctly? Or do we have to do greater than 0? Let's just see what we get, what's wrong with that. The 0 flag is wrong and the carry flag is wrong. So it looks like the other one is correct. If I take that off, is it still incorrect? No, it looks like that might have worked. Yeah, the negative flag is correct, just like that. So I'll probably get rid of these brackets as well, can I? Yeah. Okay. So that's setting the negative flag correctly. We also want to set the 0 flag just if A equals the operand. Okay, like that. I think that's right. Yeah, so that got rid of that error. And the carry flag is based on that the A register is greater than or equal to the operand. So maybe this is a bad name, this set 0 negative flags, because it seems that this function is setting them differently. So we might need something a bit better than that one. We'll refactor that when we get to it. So that's good, that test passes. Let's just see if we can put some more tests in, and we can put some more of these ones in that they've got here. So the second example, what is this one? It's adding, this one adds 48 to 26. I don't know if this is a very similar test to the other one. No, it's not, because the 0 flag is not set. Compare, so this is compared to different values. So let's just say that, 2 different positive values. I'll just say it can compare our large positive to our small positive. So they want the 0, negative and carry to be false before, so I'll set them all to true before. Oh no, is that? Why does that make any difference what it is before? It might do. Yeah, I don't think that really makes any difference to us what these are before, because it doesn't bother with them. I don't think it does anyway. I think that's just negative for no particular reason. In the third example, the number began as negative with the negative flag set. I think it just doesn't matter. They're just proving that it got cleared. They're kind of doing what I'm doing, which is setting things to the opposite of what they should be, just to prove a point. So in this case, I actually want to set it to the opposite of these flags here. So this is 0. Let's order it the same again like that. So let's set it to true, true, false. Let's just see if that's right. It's still, yeah, it's always 2 cycles. So what do we expect? We still expect the A register to be 48. It's not changed. We expect, I mean, this might be that these tests are basically kind of like what we did with the other one, where we just have, we want to keep repeating the test, but this is so simple, maybe we don't need to do that. I don't know. So the 0 flag is set if they are the same and they are not the same. So that doesn't get set. The negative flag should be set if bit 7 of the result is set, and it's a positive number, so it can't be negative, so that's got to be false. And the carry flag is set to true because A is greater than or equal to M, which is true. So I would expect, I still think that will pass, and it does. So let's do another one of theirs. So this next one, I wonder if I should refactor these out, because we're going to have to repeat these for different memory modes. I don't know. The number began as negative, so 130. So the A register is 130, and then we're going to subtract 26 again. I can compare a negative number so we're just going to compare a negative to a positive. So that's a negative value there. That is a negative number. So we still expect that value, whatever it was, to be in the A register at the start. So what do we expect then? 0 if they are the same. They are not the same. Negative if the negative flag was set. Now this is the interesting one. You'll end up with 130. Let's put this in byte mode just to be sure. I can't put 130 in byte mode because it's signed. Let's do it as a word. 130 minus 26. Hello? Is 104, which is not, would be considered a positive number in the 6502. So negative is going to be false, and the carry is set if A is greater than or equal to M. So this is the weird thing. If the A register had a signed number in it, it would actually be less than 26 because this would be negative. But if you're treating it as signed, it would be greater. So the comparison always treats it as signed. That's what basically this page is saying, that comparison is a signed comparison. So this is greater even though it's negative. So the carry flag gets set to true, and the negative flag got set to false. So basically it's not signed. That's what we're saying. So in theory, I think this still passes as well, which it does. There's a lot of tests in here now. 180 tests. So that's all good, and we've got one last one that they've got here, which is, yeah, and that's what they're saying there, is what I'm saying, that like it's just being done signed. This doesn't mention the fact that this is not a signed comparison. It's an unsigned comparison. Maybe you're supposed to just know that, I don't know. This last one sets the negative bit, so we should do that one as well. This one can compare two values that result in a negative. Okay. So set the negative flag to false and set the others to true. And what's this value? This is A register being 8. Is that right? A register being 8. And you subtract 26. Yeah, so that produces a negative number. Okay. So yeah, 8 minus 26 would be negative. A register should still be 8. The 0 flag, again, what is it again? 0 flag is set if they're the same. They are not the same. The negative flag is going to get set because the result is going to be, what's that? 12, 18, is that right? Yeah, maybe negative 18. So the negative flag's going to get set, and the carry flag gets set if A is greater than or equal to M, and A is not, so that's false. So those are some quite good examples. That shows you why you can have this thing written, it seems dead simple until you actually try and write it out, and you're like, oh, we've got all these weird cases that happen. That still passes, I think. Oh, that didn't pass. Did I get the test wrong? Why is that? Where's the test? Okay. Got so many tests it just scrolls off the window. What are we getting? Negative flag, actual false, expected true. So 8 minus 26. Have I got this? Have I got the test right? That's the question. Yeah, so it didn't set the negative flag correctly. Okay, so let's just go in and let's go in and have a look at that. What's on here? So we get the operand is 1A. So we get the operand as 1A, which is 26. We do that, we get 238. And this is where, yeah, the negative flag, that's the bit, that shouldn't be happening, should it? Because that temp, that 238. This is the bit where I need to put in 238 and then set it to byte. Is that right? What is that in? Yeah, it won't let me put in 238 because it assumes that these are signed. 2, 3. Oh, yeah, I'm putting that in decimal. I mean, 238 there has got that bit set. So that's wrong. I think this is where something to do with these bit fields has kind of made this a bit screwy. Let's just see if I do that, if it passes. Oops. Yeah, it does. So that, I was thinking I didn't need that greater than 0, but I do because I've got something to do with the fact that this is this bit field and it doesn't work correctly if you just do it like that. Yeah, I mean, I could do that by shifting right as well, but I'm not going to do that. I'm just going to do greater than 0. That's pretty good. I think that is immediate mode done for that. I'll tell you what, maybe I'll leave it there, and then in the next video we'll do tidy up and do the rest of the addressing modes. So yeah, next video I'll do the rest of the addressing modes, and maybe I'll refactor these tests so that we can keep reusing them a bit like we did on that other one. But we'll do that in the next one.